Hello everyone, welcome back to my channel again. Today I came back with another important video from the chapter oscillation is that simple harmonic motion as the projection of uniform circular motion. That means I just want to relate between the SHM simple harmonic motion and UCM uniform circular motion. First of all, I have drawn a circle. Let's assume an object is revolving or rotating around a point with a uniform circular motion. If we draw the diameter of the circle, in this case, this is the center. Okay, center I am taking as O. So let particle or the object is rotating in an uniform circular motion with an angular velocity omega. Now try to understand one thing, how we can relate them actually. So when particle is coming in this point, what is the shadow of this particle? Shadow means the projection will fall on the diameter in this position. When particle reaches in this point, the shadow will fall here. So when the particle reaches in this point, the shadow or the projection of the particle will be falling on the diameter in this point. So in this way you can see at each and every point, if we draw the projection of the particle is actually moving in a circular path. Try to understand, particle is actually moving in a circular path, but its projection, if we assume it is going in a straight line path, in the first half circle it is going from right to left. You can see when the particle is here, it is the position of the projection of the particle. This is the projection of the particle. This is the projection of the particle. Means gradually the projection of the particle is coming in the left side when the particle is moving in the upper half cycle. Now what will happen when the particle reaches in the lower half cycle? In the lower half cycle, when the particle reaches here, the projection of the particle will on the diameter is over here. When the particle is here, the diameter on the projection of the diameter is in this point. So when the particle is coming here, you can see the projection of the particle is falling on the diameter in this point. In this way, in the lower half cycle, what will happen? That the projection is actually moving from left to right. So try to understand once again. Particle is actually moving in a circular track, circular path, but in every point its projection is just like you can assume like a shadow. The shadow of the particle is falling on the diameter in this point. So that means when the particle is gradually moving anti-clockwise from the upper half cycle, the projection is at each and every point, projection is coming in the right to left. Now for the lower half cycle, the projection again going from the left to right. So that means particle is moving. So that means the particle is having uniform circular motion, but projection of particle is nothing but, what is that? Projection of particle is basically, projection is once coming in this direction, then again coming in this direction. That means it's a kind of oscillation, you can say. That means it's kind of simple harmonic motion. So that means projection of particle is a simple harmonic motion. Okay, so that is the relation between the uniform circular motion and simple harmonic motion. So actually in reality the particle is in circular motion, but its projection, its shadow, every time it is going once from right to left, again left to right, right to left, left to right. That means this kind of thing is happening at point O. It is going from the point O. If I draw from the point O, it is going from right side, again left side, again right side, again left side. That means it's kind of a wave is forming, right? That's why it is called oscillation. So that means projection of particle is a oscillation, that is called simple harmonic motion. Original particle, uniform circular motion, but projection of particle, simple harmonic motion along the diameter. Okay, so you can draw I have drawn the horizontal diameter, you can draw the vertical diameter also, right? So this is how we can relate the motion of a particle and its projection, or we can relate between the simple harmonic motion and the uniform circular motion. Okay, remember when the particle is at the middle point, if we draw, you can see, if we draw a wave, okay, if we draw a wave, okay, for vibration, what is the main under this line is called mean position. So from the mean position, this is the point is known as mean position, and this is the extreme position, which is also called as amplitude, you know that. So that means from the mean position to the extreme position, again this extreme, again zero, again extreme, like this the wave is forming, right? So now you can see this O position is nothing but the mean position. O is the mean position, and if we consider a point, let's assume B, so that means this B position is known as the extreme position, Okay, so that means from the mean position it is going to the positive extreme, then again negative extreme. In this way a wave is forming, like it's a wave is forming. So in this way basically the wave is forming from the mean to the maximum, negative maximum, like this way a wave is forming. That is how we can relate the simple harmonic motion and uniform circular motion together.
Now you can see next topic is the displacement calculation from the uniform circular motion with the how to calculate the displacement in uniform circular motion. First of all, so let assume there are three cases we will do first. Okay, first case is that the case number 1 when there is no initial phase, means where the object or particle supposed to be start, the object or particle is starting from that point only. That means there is no any advancement or delay of the particle starting point, right? So first case is that case number 1, if an object or particle is rotating with respect to a central point, that central point is considered as a mean position. So with respect to mean position, the object is rotating in a circular motion with a angular velocity omega. Okay, now what will happen, you can see here. So first we will draw the diameter of it, and as I said, the particle actually having a rotational motion, but the projection of the particle is having a simple harmonic motion. Projection of particle is actually moving from left right combination. That means when it is going sometimes from left to right and right to left, okay, alternatively. That is it is called simple harmonic motion, right? So now so case number 1, when there is no initial phase, that means phase difference phi naught is called initial phase, which is 0, right? So how to find out? Suppose at t equals to 0, the particle at, this is the O particle, is at point B. Now after at time t, the particle, let assume the particle reaches this point P. So particle has been reached to point P. That means how much from the mean position is, this is the displacement. So what is the displacement? Displacement is nothing but you have to draw the normal from the point P on the diameter, and the normal is cutting on the point N, touching the point N, right? So now this is the displacement A O N, this is the x is the displacement over here. So now how to find out? As I said, this is the extreme position, this is the mean position. So as this is the extreme position, that means I can say this is also extreme position. From the mean to the extreme, the distance is called maximum displacement, which is also called as amplitude. So that means this is an amplitude, this is the amplitude, right? This is the amplitude. Now how to find out the displacement x, because it is because the heading is displacement calculation in an uniform circular motion. So how to calculate? Let me show you that how to calculate this. First of all, so ON I have to find out if the angle is theta. Here the theta, we know in case of angular motion the theta is equals to omega t. Theta is equals to omega t. How it is finding? That omega means angular velocity, angular velocity means angular displacement upon time. That therefore theta is equals to omega t. It is coming, right? Now I will take this triangle PON. It is a right angle triangle because PN is the normal on the diameter, right? So as this is the angle is 90-degree angle, right angles, right? So that means in triangle PON, it is a right angle triangle, it is a right angle triangle. So in this case, in a right angle triangle PON, so what is this triangle? I will do the cos theta equals to, so cos of theta. Cos theta means we know base upon hypotenuse, base upon hypotenuse. So if it is the theta, so base is ON, ON is the base, and hypotenuse is OP. So ON by OP, ON by OP is the cos theta, right? So now cos theta ON, ON is the displacement x, and OP is the maximum displacement, which is also called as amplitude. Now cos of theta equals to x by a, I am getting from this figure. Now theta means again omega t, so that therefore I can write x is equals to a cos theta, or x is equals to a cos omega t. That means this is the displacement expression for the uniform circular motion. This is the first case. Second case, case number 2, when the phase difference is positive, that means the particle already well in advance. That means let assume in a circular motion, in this circular motion Okay, so let us assume this is the circular motion. The particle at time t equals to 0, the particle was at point B, already some angle it has been occupied initially, that means this is the phi naught, this is the phi naught, right? So now this angle is the phi naught, this is the O. Now at time t, it is reaches at time t, it reaches the point P. So how much displacement it has been taken? It's nothing but the amplitude A. So what is the displacement? You have to draw the normal from the P to the diameter, that is ON. ON is the displacement here, same concept. ON is the displacement X. I need to find out. So how much angle it has been occupied, that is nothing but at from t equals to 0 to t equals to t, that is the theta, and theta is equals to omega t, we know already. Theta means omega t, so therefore theta is equals to omega t, we already know this. Now cos theta, so in this again, in this triangle PON, this is a right angle triangle, PON is a right angle triangle, so we will find out cos of what? Cos of theta plus phi naught, because PON, angle PON is a right angle, angle PON, this is nothing but omega t plus phi naught, because this upper angle is omega t and the lower angle, this part is phi naught. So therefore I can say cos of omega t plus phi naught. Cos of the whole angle is nothing but again base by hypotenuse, base upon hypotenuse, base is ON, hypotenuse is OP, so ON is X, OP is A. So therefore from here I am getting another expression, A cos omega t plus phi naught. So this is the expression for displacement from the uniform circular motion. That means directly we know this is the expression for simple harmonic motion, displacement expression for simple harmonic motion, right? But I am now I am finding out from the circle, means uniform circular motion, right? And the case number 3 case number 3 is when the phi naught is negative, that means already particle is in delay, it is not in advance, it is in delay. That means the particle, let us assume this is the center. Okay, the particle at t equals to 0, here it is the B point, initially the point was here, that means this is the, you can say this is the phi naught, but there is a negative phi naught because right side or and clockwise angle is known as negative angle. So suppose at time t equals to 0 point, particle was here, now particle due to the circular motion, at time t particle reaches this point P. So how much angle it has been occupied, that is the total angle is nothing but omega t, total angle is omega t. Why omega t? Because theta means how much angle it has been covered, that is nothing but angular velocity multiplied by time. Velocity into time is called angular displacement. So how much angular displacement takes place, that is nothing but theta. So what is this angle? If we draw a normal from point P on the diameter N, so this is the ON is the actual displacement X. So in this case, if this is the amplitude we know already, right? So in this case, the third case number 3, triangle PON is a right angle triangle. So in this case, what is this PON angle is equals to? Angle PON is nothing but the whole angle omega t minus phi naught, because I want to get only this much of angle, only this much means the total minus phi naught, that means total is omega t minus phi naught. Okay, now again I will apply this cos theta formula. So cos of omega t minus phi naught, that means cos of this angle from this right angle triangle, cos of this angle is equals to base upon hypotenuse. Base means ON, hypotenuse is OP. So ON means X, hypotenuse A. So therefore I am getting the expression A cos omega t minus phi naught. So this is the expression for displacement. So there are three cases of displacement. Sometimes the particle are having zero initial phase, then displacement is only a cos omega t. Sometimes the particle well in advance, that means particle is already some angle has been occupied initially, that means some initial phase has been added with the original angle. Sometimes the particle are delayed. Actually particle is supposed to start from here, but the particle is delayed, means particle was here. In that case, that is a minus sign. So the ultimate formula we are getting x is equals to a cos omega t plus minus phi naught. This is the expression for displacement. Sometimes phi naught can be 0 for zero initial phase, sometimes phi naught can be positive, sometimes phi naught can be negative also. So that therefore this is the overall expression of displacement for uniform circular motion. Okay, so I hope you understood, very easy concept. Just what I am doing, I am just drawing the projection of a particle on the diameter, and the projection of the particle is touching the diameter at a particular point n. So I am getting a right angle triangle. In every cases you can find I am getting a right angle triangle, and in right angle triangle cos theta equals to base upon hypotenuse. Cos theta means for this right angle triangle, try to understand this angle is important. That means this angle I am talking about, only this angle. I am talking about this angle. I am talking about this angle. This is only important. Okay, cos of theta will do, and we will easily calculate from displacement expression from the uniform circular motion. Okay, so I hope you understood. Now we will do the next topic, that is the velocity of uniform circular motion. Look how to calculate the velocity in uniform circular motion. So in this case you can see I have drawn a circle, and in this circular path the particle is moving in anti-clockwise with an angular velocity omega. Let us assume the angular velocity is omega. Okay, now how the particle is moving, basically in case of circular motion, at each and every point of a circular path the velocity is always tangential, right? Always tangential. For example, from this point, for this point, if I consider this point, that it is always tangential. So tangential velocity, why? Because you know, in case of circular motion, at each and every point the velocity direction is continuously changes. That is the reason why it is also called accelerated motion. Although it is an uniform motion, uniform means speed is constant, but the velocity is continuously changes. And why it is changes? Because the direction changes. As the direction changes, that's why I can say the acceleration is there. That means it is an accelerated motion. So in this case also same case. So if I consider at a certain time the particle P at a particular point, particle is at point P, and what is the direction of velocity along the tangent of it. Now just we will join this. This is the diameter. Okay, this is the diameter. This point is O. Now what will happen, that if we do the component division of any vector, component division of vector means, suppose this is the vector, we can divide into two components. One is called vertical component, another is called horizontal component, right? So suppose this is the A vector, so if it is theta, so then it becomes A cos theta, and it is the A sin theta, as you know already, right? So in this case also same thing, that it is the velocity vector. Velocity vector I will be dividing into two components. It is the horizontal component and it is the vertical component. Okay, horizontal and vertical component. Now, and this angle is theta, I am taking as theta. So if it is theta, so here theta means I am just taking as omega t plus phi naught. Theta is equals to I am taking as omega t plus phi naught. So now if it is theta, it is also theta because of alternate angle. Because of alternate angle, if it is theta, it will be also theta. And as it is theta, the upper part, this one is also theta. Okay, so that means if this part is theta, so the component which is connected with the theta is called cos theta component, and the component which is not connected with the theta is known as sin theta component. Now as the V component is connected with the theta, in this component is connected with the V theta, that's why this is the V cos theta, and the horizontal left hand side component is known as V sin theta, right? So in this equation, in this calculation of velocity, we are not bothering about the vertical component, because ultimately the projection of the particle is in the horizontal line, right? Ultimately the projection of the particle is in the horizontal movement, right? That is the reason why I will be only taking care of the horizontal movement of the velocity. That means only velocity which is along the horizontal line I will take here for calculation purpose. So let's have a look how to solve this. So velocity along the horizontally, and this is the velocity component and it is acting in the left hand side. Anything showing in the left hand side is taken as a negative. Remember, showing in the that means anything is directed towards the left hand side is considered as a negative. So that's why it will be minus v, and as it is sin theta, so it is the sin theta. So actual velocity component along horizontally is nothing but minus v sin theta. And we know in case of circular motion, if omega is the angular velocity, r is the radius of the circle, in that case what will happen, that v equals to omega r or r cross omega basically. So v equals to omega r. So here r is radius, but in this case, in this figure, this is called amplitude. So here amplitude itself the radius for uniform circular motion. So I will write down v equals to omega a. Okay, so instead of this I will write omega a sine of theta, and as the theta is omega t plus phi naught, so therefore the velocity component is nothing but minus omega a sine omega t plus phi naught. So you are getting this expression of velocity, expression from the uniform circular motion. How to calculate this with the help of differentiation? Let me show you. As we know, the displacement expression we already got, a cos of omega t plus phi naught. This is the displacement of the particle at a certain time t. That is the formula. So what is the velocity is equals to? That is equals to dx by dt. Rate of change of displacement is known as velocity. As we know, the differentiation of cos is minus sine. So minus a is a constant. So write down here cos is become sine omega t plus phi naught. Okay, but as I am differentiating with respect to time, so whatever is added with the time means omega is taken as a constant, and that will be coming out. That's why minus omega is sine omega t plus phi naught. This is the velocity expression by differentiation. This is the velocity expression I have calculated from the uniform circular motion, and this is the velocity expression by using the derivation of the displacement, right? So you can see both are same actually, right? So this is how you have to calculate the velocity in uniform circular motion. Now next topic is the acceleration in uniform circular motion. Calculation of acceleration in uniform circular motion. Let us assume an object is moving in a circular track. Okay, an object is moving in a circular track. Okay, now you know what the direction of acceleration is most important part. Direction of acceleration is always towards the center. That is also known as centripetal acceleration, right? So any direction that suppose the particle at a certain time is over here. Now particle acceleration is always acting towards the center. Remember, acceleration always act towards the center. This is the acceleration small a. This is the vector quantity that is known as centripetal acceleration. Now in that case, same concept will arise. We will do that the vector component division of vector. Suppose if any vector is showing in this direction, how to divide in two components. One is called vertical component, this one, another is called horizontal component. So thus in this way we can break or we can split a vector into two parts. One is called horizontal component, another is called vertical component. Okay, chalo, this is the acceleration, this is the point O. So now how to differentiate this acceleration, how to calculate this acceleration? So I am just first breaking down into two parts. This acceleration I am just taking into two parts. One is
vertically downward, another is horizontal in the left side. Okay, so if I am taking this angle as a theta, so we are same theta is equals to omega t plus phi naught. This is the theta equals to, right, omega t plus phi naught. So if it is theta, it is also theta. It is also theta. Why? Because the alternate angle. So if this is the acceleration, so this will become as a cos theta, and this will become as a sin theta, because the component which is touching with the theta, that is become cos theta, which is not touching with the theta, that is called sin theta component. So what we are talking about, we are only talking about the projection of the particle, and you can see the projection of the particle is along the horizontal only. There is no concept of vertical is here in this as per the figure, right? So that's why we will ignore the vertical part only. We will just take the horizontal part. Horizontal component of acceleration only has to be taken. Remember, there is no requirement to take the vertical component, because we are just talking about the particle movement in a horizontal, means projection of particle. Projection of particle is moving along the diameter, right, like horizontally. That's why acceleration only has to be taken in horizontally. Remember that. So acceleration along the horizontal axis is equals to, what can I write? A acceleration cos theta, and you can see here, as it is acting in the left hand side, anything showing in the left hand side taken as a minus, remember, taken as a negative. Anything showing in the right hand side taken as a positive. So as it is, acceleration A cos theta is in the left hand side oriented, that's why there will be a minus sign, so this will be minus A cos theta, and we know what is the relation between the acceleration and omega. Omega means angular velocity. So this is the relation. A equals to, we know, omega square r. A equals to omega square r. Omega is the angular velocity, r is the radius. In this figure, this amplitude itself the radius, okay, this is the mean position, extreme position, the amplitude itself the radius. So I can write as, it is nothing but omega square A. Instead of radius r, I can write as omega square A. This is the formula we can get from uniform circular motion calculation, right? Acceleration equals to omega square A, right? Now put the value over here. Now minus omega square A cos of theta. Theta means omega t plus phi naught. Therefore the main acceleration expression is nothing but minus omega square A cos of omega t plus phi naught. So this is the ultimate expression for acceleration. Remember. So how to find out? Again, x is equals to A cos omega t plus phi naught. When we differentiate with respect to time, we will get the velocity, and velocity what we got last time, omega is coming out as a minus sign, because the differentiation of cos is minus sign. So minus sign omega t plus phi naught was the expression for velocity. Now again we will differentiate dv by dt, which is also called as acceleration, or you can do the double derivative of displacement, also called acceleration. Now omega a is a constant, minus is constant, sin का derivative होगा cos, so cos of omega t plus phi naught. As we are differentiating again with respect to time, so time with time omega is there, omega again come out, so it is minus omega square a cos, and a cos this is nothing but the x, so therefore I am getting the expression minus omega square x, acceleration equals to minus omega square x. So this is the, by differentiation I am getting the expression for acceleration, and this is by the uniform circular motion I am getting the expression, and you can see both are equal, both are same actually, right? So this is how we can relate the uniform circular motion with simple harmonic motion. Okay, so this is all about the expression, calculation of displacement, velocity, acceleration, okay, one by one. So that's all for today in this video.